speak about ferromagnetic semiconductors as localization boundary. The work was done with my colleagues in Warsaw, and after we have long-standing collaboration with Sendai, and the results were actually taken to Europe. And as I refer to the results taken in Regensburg, so the question actually is as called as P5 semiconductors, because even from fields where we knew very well that we are localization here is resistance plotted as a function of temperature, it is clearly seen that in some samples this resistance goes to infinity, meaning that the samples are on the insulating side of the transition, whereas other samples extrapolating the resistance with finite value. So somehow physics of these materials is actually physics of the boundary of the insulator transition. Also, if you go to other systems like 2,6 docked with nitrogen to produce holes, and docked with manganese to produce magnetism, we see that at high concentration we are entirely fast with the work, whereas at lower concentration of nitrogen or phosphorus dopants we are at insulating side. Well, actually, this point is much older. You think what is actually trademark of semiconductors, ferromagnetic semiconductors, is just giant, huge temperature and magnetic field dependencies. Somehow you see this huge negative magnetic resistance data, that's not data 0 Tesla. So this colossal negative magnetic resistance and localization effects depending on magnetism are kind of very well known and very old in the various magnetic semiconductors, especially ferromagnetic. And we see at once that if you order either by transition to ferromagnetic phase, this means, or we order the paramagnetic material by putting strong magnetic field, we see that actually we have low resistance. So magnetic order promotes metal phase, whereas disorder, magnetic disorder promotes insulating phase. And actually this is well known from colossal negative magnetic resistance systems like manganite, that application of the magnetic field orders or ordering phase at low temperature also make that the resistance is lower, whereas near phase transition, which means on disorders, when disorders localization has stronger resistance. And now the question is where is this metal insulator transition occurs in normal semiconductors? Actually, in normal semiconductors we know very well that this transition occurs depending on the ratio of both radius, or radius which depends on effective mass of the electric constant, and actually it occurs when average distance between electrons or holes is about 2 times bigger than order. This is effective order. We can recalculate that actually following this paper, and you can convince ourselves that this corresponds to the situation where Fermi energy calculated without any disorder, just for free electron, is equal to something like 0.6 of ionization energy of given sample. So if you know ionization energy, and you can calculate for effective mass just Fermi energy, you can predict more or less where you are in this curve. You are at very low concentration into manganite, where effective mass is very low, or it is very high, and you can be much higher concentration at 120 gallium arsenide with manganese. So the first question is how is localization? I will answer this very general. How does this affect carrier-mediated ferromagnetism? So to have carrier-mediated ferromagnetism, we need carriers by definition. And actually, if we go to materials as carriers, we can understand very well chemical trends. What you see here is reported highs, reported gallium arsenide, gallium phosphide, and other material PCs compared what you expect theoretically. And actually, in this material where you have holes, you do see kind of agreement with this chemical trends. This can be done do artificial, can do analytically using model Hamiltonians. But everybody agrees if we have carriers now, we can understand the ferromagnetism. But what happened when we go to other materials? As you saw, this plot didn't show, for instance, gallium nitride. So what happened with gallium nitride? If you go to gallium nitride and we start to look on experimental value of ionization energy, how actually, what is thermal activation energy to excite holes to the valence band, we see that it's huge in case of gallium nitride. So this parameter which determines metal insulator transition very large. So we need extremely high Fermi energy to be on metal side of the metal-insulator transition. So not astonishingly, we have no carriers. There's no p-dab gallium nitride up to this manganese up to now. And therefore, we expect no ferromagnetism. We actually expect that here in this gallium nitride or zinc oxide with manganese, we have high manganese ionization energy. So there is region where actually we are on the isolator side of metallic isolator transition. And the nose is carrying negative ferromagnetism. Expect the contrary to, let's say, indoor-antimonal like gallium arsenide, where you have bigger chance to be over metallic isolator transition and have this kind of negative ferromagnetism present. And indeed, if you go to gallium nitride now with manganese, what you see is that maybe in the 6% sample there is a very small TC of the order of 8K, despite a relatively high manganese concentration. And ab initio calculation shows that indeed the material TC should be very low, and the reason is there is no carriers or there may be ferromagnetic superexchange here, for example, double exchange. Now we go a little more into details. We were just now very phenomenological. We use empirical rule which shows where this is metal-insulated transition. The base of this empirical rule, we said that some materials we expect magnetic phase because carriers could be present. In other cases where this ionization energy of acceptors is very high, we do not accept ferromagnetic carriers because there is no metal-insulator transition. We are on the isolating side of the transition. But now we ask the question, what is the nature of this transition? A little bit we want to be more physical. And the nature of this transition, I think there is agreement in communities, Anderson-Mott type. What does mean? It's kind of name, but what does means? And we know that it means that there are two very important ingredients which has to be simultaneously taken into account. One of them is disorder, obviously present because we have a random distribution. Doping centers and correlation. We cannot take one and forget about the other. Both are equally important. And this was very strongly studied in the 80s, and this kind of, in some cases, well understood. Okay, so we said that disorder is important, correlation is important, but what is more precisely going on, we have to take into account quantum interference. Remember, Anderson's paper was the absence of quantum diffusion. So quantum effects like quantum interference are still important. We have to take, as far as correlation is concerned, we have to take into account interference interaction amplitudes induced by the presence of disorder. And third, very important ingredient, which actually we see very clearly established because of conductance fluctuation and other phenomena, is presence of mesoscopic fluctuation density, local density of states. So there are three gradients which are very important in any material, in particular in magnetic semiconductors, which contains dopants and contains carriers. And in this kind of materials, actually, these interferences, fluctuations, are strongly affected by spin order, by the presence of spin order. Experimental things we saw that when we have spin order, we have metal insulator transition, but also the point I did, right, that also they strongly affect spin order. So there's mutual effect between presence of spins and this reason for metal insulator transition in semiconductor. And I mentioned quantum interference as well now, but just to recall me that in crystals we have certain energies, say the K-vector into constructive interference, black conditions, we have possibility of quantum diffusion. You know, it's very true. This quantum interference are very deeply rooted in presence. It's the fact that we have bands and that the electron can move in quasi-free way in certain region of energy. But what happens if we destroy this kind of coherence crystal structure? We have disorder. If we have disorder, instead of interference are again very important, but this time interference gives rise to localization. So completely different effect of interference compared to crystal. And why is it give to localization interference? It's very famous as backscattering problems that if you ask the question, we have scattered electron, but electron can scatter on many impurities, which I will draw here. There are many impurities which lead that electron can come back to the starting point. We have no impurities, electrons starting from one point go away and never come back to the starting point. But having impurities, there is finite probability that electron will come back, and this enhancement of the fact that we have interference for that trajectory, that quantum interference, this is enhancement by factor of 2. This probability makes that localization is enhanced, this transition probability to static points enhanced, which enhances localization, and at the end gives actually isolating phase. And we can crop presence of that using magnetic field. We put magnetic field crossing the flux here, we affect interference, and we have destruction of this interference actually, and this gives rise to negative magnetic resistance. And this is very universal phenomenon. And if you are in gallium manganese arsenide, this polarized manganese spins by being at low temperature, and at the same time putting magnetic field, nothing happens with magnetic order, spins are ordered, but still we see negative magnetic resistance going on up to 30 Tesla, and zero is that curve. Nobody explains this mathematically with logic parameters, assuming that valid genesis is 1, which is quite normal for this almost half metal situation. And now, what about electron? This is correlation. We said that correlation are also important. In case of correlation, we have no disorder, electrons interact, two electrons go away, never meet again. But if we have disorder, electron trajectory is very complex, so it's diffusive way, and there is finite probability that electrons will meet again and again and again. And we have now this interaction amplitudes, again, not probabilities but amplitudes, and altogether makes that we have diffusion, which can be reduced or enhanced, but importantly we have also Coulomb anomaly and the Fermi emergent, very interesting temperature dependence of resistance. So resistance here, this temperature dependence, the limit of low temperature observed by many people is actually associated with this presence of interaction. And here you see very beautiful work in one dimension. Theory predicts this dependence, it's observed experimentally, plot 1/t². In one dimension, two dimensions, logarithmic temperature dependence expected in three dimensions, square root temperature dependence. Everything fits very well. And actually from Z slopes, you can do training what is the amplitude of interaction, and it's a very important factor because it's exactly the factor which determines enhancement of Zener ferromagnetic by Stoner. We were using in all our calculations this value 1.2 according to this experiment 1.4, which is kind of reasonable. One can argue why it is a little better to use a little smaller at no time. But anyhow, altogether fits what was expected. The Stoner effect is also important, and actually the Stoner factor now is just better. And also Coulomb gap is better. People see Coulomb gap in this very nice experiment done first in Pittsburgh, but now there's a beautiful experiment done in Princeton. And actually, I will discuss this other experiment in connection with this problem, fluctuation, local density of state. So what is the fluctuation, local fluctuation of density of state? If we go to insulating side, we have impurity, strong disorder, we have Poisson distribution more or less of levels. If we take certain region of space and count number of levels, it will be a master region and good for distribution, it will be Poisson. If we go to metal, actually there is strong correlation between levels, and we go to linear distribution, but if we go to metal, isolator transition region, we have kind of in between, we have huge kind of formation of cluster and large local density of states, which, as I said, is very beautiful because of conductance calculations. But also nowadays, we can see by scanning panel microscopic work at Princeton, in collaboration with Santa Barbara, the challenges here, and this work shows beautifully that we have this fluctuation local density of states, and actually this local fluctuation density of states is visible here, and also what is visible here, it samples with different concentrations, so we have strong Osaka localization, weaker localization, still weaker, and this data were taken as a Fermi energy, and this also represents Coulomb gap, that if you have very little states, big Coulomb gap, low densities of carriers, remember that was an acceptor, we have a little higher density of states, at the medium concentration of the metallic state, we have much higher density of states. But important point also is that we see that this local density of states fluctuates. And this has an enormous effect on magnetic properties, because if we have locally more carriers, we will have locally more order, magnetic order. So what we can, looking at this kind of picture, we can suspect that we have kind of local superpramagnetic grain, which we can order if we go to low temperature, or we can order them if we go to high magnetic field. So this kind of result immediately demonstrates that we should take into account very seriously the presence of what we call phase separation, nanoscale phase separation to regions which are more polarized and regions which are less polarized. And this region may be disordered at higher temperature and more ordered at lower temperature field. And actually, this we believe that the presence of this region beautifully visualized by this STM, where the source of strong spin-dependent scattering LTC. We believe now that critical scattering, colossal negative magnetic resistance associated with it, is associated with the fact that near TC we have this long-range possibility of scattering of holes or electrons in other materials by the presence of this nanoscale grains. And also, of course, there's this one, but also very important, if you now measure transport, you have metallic grains, so you can have Coulomb blockade. You have kind of quantum dots. Here you have more carriers, around less carriers, so you may have effects associated with Coulomb blockade. And also you may have effects which is associated with the fact that if you make transport, you penetrate all of these metallic grains, so you have beautifully, you measure on scholar, and you have beautiful hysteresis because you probe all the real ferromagnet where you have carriers, but if you measure now magnetization, you see completely different hysteresis. Why? Because magnetization, you also probe this region which are less oriented. So this experiment also confirming a sense the difference between transport signatures and the magnetic signature of ferromagnetism that we have in homogeneous system. And this is quantum dots, this kind of presence of dots on nanocluster is seen also as Coulomb blockade. I mentioned the possibility. Here you have two experiments with nanoconstrictions, which shows if you change gate voltage and the number of electrons in the system on holes in this case, you see this Coulomb blockade peaks. And this Coulomb blockade now can be explained that you have this nanoscale phase separation I refer to. Here you have this critical scattering LTC, which is lower if you put on magnetic field. And he explains this critical scattering in the sense that we have this grain which starts to be ordered either at the lower temperature or the magnetic field on. And I mentioned that we have this superpramagnetic, ferromagnetic grain superimposed. And do we have experimental evidence for that? Yes. If you do very carefully measurements of samples close to metal insulator transition, you will see that you have reversible contribution from ferromagnetic phase, but also you have irreversibility at low temperatures that you see. Irreversibility that actual magnetization depends on the keystone that you start to cool down and go in magnetic field or without magnetic field, you without a different curve. Actually, you can do standard superpramagnetic wave study, and you will convince yourself that you have superposition of ferromagnetic waves, but also superpramagnetic contribution. So we have kind of two fluid system. And we can visualize that also, we can study that nowadays as a function of carrier density in one sample, the same sample. One can nowadays, he developed this technology in Sendai. Actually what he did, he measured directly magnetization as a function of the electric field in the same samples. And due to that, he can change systematically carrier density and see how this superparammagnetism and ferromagnetism evolve. And then shown here, what you see here is magnetization plotted as a function of temperature for several gate voltages. Here we have a lot of holes, gate voltage is negative. Here we have fewer concentration of holes because gate voltage is positive. So we can observe what is going on with saturation magnetization, what is going with TC, and we can now analyze how much of ferromagnetism, how much of superparamagnetism we have here. And this analysis is a little complex, but what you see here is just comparison how the superparamagnetic term, superparamagnetic contribution depends on gate voltage. What happens if change gate voltage actually is plotted for various orientation of the magnetic field to see contribution from region oriented in different crystallographic direction. And the message from this kind of measurements is that this contribution of this relative contribution of the superparamagnetic is increasing. If we deplete the channel, we have more and more the superparamagnetic contribution. And also we see that the size of the superparamagnetic region decreases if we deplete the channel of holes. And also we see, if we analyze this curve, we see randomization of the easy axis. In ferromagnetic case, we have this material very well defined easy axis to make this material more superparamagnetic. Less. So what would be kind of maybe conclusion from what I said from here, that transition from ferromagnets to paramagnets, so without holes we have paramagnet, with a lot of holes we have superparamagnet, we have ferromagnet, but in between we go through kind of superparamagnetic phases. Locally we have ferromagnetic over there. So the question how ferromagnetic disappear is a question how locally the system looks like, and then now it's not that we have homogeneous ferromagnets and we jump to homogeneous paramagnet, we go through kind of superparamagnetic phase of all this. And now we said that it's a very complex system and there's a lot of this localization, there's a lot of fluctuation. Resistance very, very strongly affected by that. The point I would like to make is that despite of this, we can, to large accuracy, calculate thermodynamic properties forgetting about this order. Actually, from physics of metal isolator transition is well known that thermodynamic properties like specific heat, electrospecific heat, Pauli susceptibility, and so on, does not feel localization. Very strong contrast to transport phenomena. Actually, what is shown that they occur moderate renormalization, random renormalization, Fermi liquid of heat capacitance, Pauli susceptibility, and so on, but there is no any divergences or critical behavior. So despite of that, thermodynamic properties can be calculated. And for instance, from this transport measurements, we can determine thermodynamic density of states. So how concentration changes if we change Fermi energy. Very different from this tunneling density of state, which says us how density of state changes if we add electron to the system or take electron to the system. Now we look how concentration changes as we change Fermi energy. And this can be calculated from this temperature dependent of resistance. And you have here comparison with various models. And the point here is that actually free electrons assuming no, models assuming no disorder, actually time binding KP are very different, quite reasonably described despite of this disorder. And you can go to another experiment, thermoelectric power. Thermoelectric power, it was shown by Mott in 1936, that thermoelectric power is more or less logarithmic derivative of conductance over energetic Fermi energy. And to first approximation, it is just, one can show it is just entropy of carriers. And actually entropy for one carrier. It depends a little bit because the derivative of kind of scattering, if you have ionized security scattering, you know that conductance actually increases with energy. We have acoustic phonon scattering, we know that conductance decreases with energy, mobility decreases with energy. And if you take gallium arsenide with beryllium at room temperature, dominating scattering mechanism acoustic phonons, and actually theoretically described with no fitting parameter is quite well. But now we go to gallium manganese arsenide, and it was changed, this is the recent work, this concentration of holes will change by bombardment with electron to produce gallium mechanisms. So to produce compensation, to produce donor which compensate manganese. And concentration was shown. Well, you can suspect that in such a case, ionizing fluid are more important because we reduce number of holes, but we add number of scattering centers. So spinning is less effective, more scattering centers because in addition to that we have donors. So we are not astonished that maybe there is this fact about 50% increase of thermoelectric power associated with present ionized here of ionized purity scattering. So this comparison show us that actually there is no big difference, and rather that picture which was used to generate these curves, this describes thermoelectric power quite resonant. I should add that there is some disagreement in experimental data. Actually, this data agree not that with first data taken north or good. There are other data taken on the reverse side, which does not show this data for no reason. And now we can understand again, I show the same plots that thermodynamic properties are not so much affected by the diffuse disorder, and therefore the theory which neglects this disorder can describe actually this results quite well. What you see again, I repeat, gallium phosphide, this manganese gallium arsenide, this manganese indium arsenide, gallium antimonide, indium antimonide. This was measured by various laboratories, highest of that order, and if you assume that it's for particular manganese concentration, whole concentration, if you assume that more or less it was that order, you have a similar trend. And this trend can be quite easily understood that what happens here, you change length structure parameters, but also you change distance between cation and anions, and therefore effectively hybridization and coupling is stronger in this material compared to indium antimonide, where lattice constant is larger. And in indium antimonide, indeed we observe much lower ETC than, for instance, gallium arsenide. And this trend can be captured and quite well understood. So this is TC, but we can go to other thermodynamic properties associated with magnetism, like magnetic anisotropy. And that's the question, what origin of anisotropy and to what extent we understand it. And there are many literature data. What I took here, what I present here, recent work done in Ulm in Munich. And this work, what you see here is an isotropy field, a field which thermomagnetization its direction applied to hard axis, plotted as a function of strain. And here you have experimental points, experimentally mean this field as a function of strain for two kinds of samples. We have annealed samples and growth samples, which is two different points. And we have also theory for this as growth samples, and process annealed samples. And here you have parameter, which is splitting, and the splitting is this samples at concentration, nominal concentration 5%, and we expect that the splitting is for 5%. The splitting is, we expect certainly this splitting, so it's a little, theory quite a little larger than 3%. And we have, as grown sample, we expect that actual concentration is lower than this observed as grown samples. Manganese concentration is partly compensated by interstitial, and the splitting by about this splitting should be taken a lot about was semiconductor agreement between several experimental machines. And this brings me to conclusions, and I would like to summarize in several parts. First, I would like to say that quantum localization effects are essential and are associated to the proximity to Anderson-Mott transition. Are very difficult to any of semiconductor, but especially this ferromagnetic semiconductors, and also negative magnetories are very close to Anderson-Mott transition. And therefore, these effects are particularly relevant. So they, what is one of the reasons of this strong influence of this quantum effect is strong influence of conductivity. This makes the temperature and magnetic field and frequency dependence of conductivity very strongly different what could be expected from Gröde-Boltzmann model. So using Gröde-Boltzmann model is very dangerous in this particular case because there is strong renormalization. Actually, to say that this effect are dramatic is enough to say that this effect exactly this quantum effect makes that resistance at some point goes to infinity. So this scaling, I mean this renormalization of conductivity or resistivity is not just small effect, but bring resistivity from finite value to infinite value. So the importance of this quantum connection cannot be underestimated. And then if we go to high temperature, but very high actually temperature, which is much higher than the Fermi energy, then this correction disappears. But if we stay in temperature, which are even room temperatures in material, remember ionization of Fermi energy of the order of 100 milli electron volt. So if we go to 300K, it's not enough to recover this quantum correction. And for instance, the meaning Hall concentration from Hall even can be wrong because this quantum correction can be very important. Even at room temperature, we try to determine Hall concentration from Hall. But going to, in principle, going to high temperature and high frequency, much larger than again Fermi energy, you can reduce the influence of these quantum corrections. And then the standard theory transport theory may work. But if with just analysis, we can have some kind of anomalous behavior, which can be caused like apparent impurity band effect and so on, because we have very unusual behavior of conductors as a function of, for instance, frequency. Then we have Coulomb anomaly and this Fermi energy. Remember, we speak here this Coulomb anomaly about tunneling of one particle density of states. One is adding electron or taking electron, and this can be seen in MTG. It is seen as kind of tunneling microscopy, and also I suggest that sooner or later, Professor Fujimori will see in photoemission experiment. Because also Coulomb gap is present in photoemission experiments. And since this experiment is pretty sure, sooner or later we will see in photoemission, but also study single electron density of state. Then another consequence of that is nanoscale phase separation in the paramagnetic low value density region and ferromagnetic region with high density. And there are many reasons that is very important. We see superpramagnetic signature in some cases close to metal-insulated transition. We see colossal negative magnetary resistance of TC, which we relate to ordering of the superpramagnetic region. We have much enhanced critical scattering is related to that. And then we have astonishing presence of Coulomb blockade in our constrictions, which is hard to understand without some inhomogeneous concentration of holes. And summary number 2, the quantum localization effects, in contrast to critical influence of transport phenomena, affects relatively weakly when it normalizes by relatively thermodynamics. Due to that, we can understand thermodynamic density of states without worrying too much about disorder. We can understand some electric power specifically, which was not yet measured, but we're interested to learn, and other thermodynamic properties. Also, we can use models which do not care too much about disorder to explain concentration, kinds of Hall concentration and TC, chemical trends, magnetic anisotropy, and magnetic stiffness and other thermodynamic properties associated with ferromagnetism. So this will conclude. The final conclusion that according to many measurements, including this measurements we did together with Hidon on metal-insulated transition and the gate, ferromagnetic disappeared on the 0% of metal-insulated transition by a gradual dominance of superparamagnetic region. So this critical transition from ferromagnet to paramagnet with a temperature which we had access to should be regarded as going through superparamagnetic